Hey you guys, here's your second installment on thermochemistry chapter 6. We're only going to do one section in this recording, chapter 6.4, and it's about enthalpy. It's about thermochemistry. The name of section 6.4 is enthalpy of chemical reactions, but it's kind of all under these headings. We're looking at what enthalpy is, so let's get right to it. Enthalpy and the first law of thermodynamics. Now, remember the first law of thermodynamics was delta U equals Q plus W. Now we're looking for this elusive enthalpy idea, and enthalpy is a word that's kind of thrown around, but it's a kind of a definition of the heat exchange during a chemical process. Now, if we have to be careful because when we have an exchange of gases, there was work done, remember. Now, if you try to keep something at constant volume and there's an exchange of gases, say you close a box and you make a reaction occur in here, and there's an exchange of gases, if it cannot expand, then the amount of energy that is building up in there and thermal energy will increase and will really not be indicative of the actual energy exchange that's occurring for that chemical process. It will be erroneously high. Now, if it is true that it's at a constant volume, the change in internal energy will be equal to the exchange of heat. Now remember, heat can be measured with a thermometer, but the only problem with that is if there is a change in volume, then that will not be accurate. So, and also constant volume is pretty hard to achieve because even if you have a closed box like this, it's still not constant volume because of the fact that this, if we look at this blob as our starting amount, there actually wasn't a constant volume. It was able to expand. So it's really hard to achieve. Now recall there's our first law of thermodynamics, but at constant pressure, pressure is easier to achieve because if we just leave it open to the atmosphere, that's constant pressure. Now we just have to take into account work if there's expansion or compression. So if you remember this picture, this was showing that a piston could move and it was at constant pressure. So then it was able to expand. And if during a chemical reaction there was a change in volume, that could be added like back into the system to account for the change in internal energy of that system. Now this Q equals delta H. This delta H is a change in enthalpy. And a change in enthalpy is defined as like a change in heat of the system as the process happens. And remember W, if there is an exchange in gaseous products or reactants, there'll be a change in volume. And when that change in volume occurs, there is work done on the system by the surroundings or vice versa. And we have to take that into account. So now what you're seeing here is some substitution fun. You know, we're saying, well, Q is now delta H and W is now P delta V. That is the change in internal energy of the system. Now we want to do a quick little rearrangement here because we say, well, what is enthalpy? Enthalpy, is it the heat? Well, it is, but it's also the exchange of internal energy of the system taking into account a change in volume. I know it sounds like this is circular. I'm just going around in circles, but we'll apply it later and hopefully that'll clear it up. Now, as far as your picture here about the snowmaking, your book has a chemistry in action about snowmaking, and the snowmaking, how this works is that there's water in here, and that water, I don't know if it's water vapor or water liquid. Water vapor, I checked on it. This is water vapor. It's compressed air and water vapor. So you have a gas in here, and you have, it's under compression to the tune of 20 atmospheres. So it's really high pressure. And then when they open the jets, it just shoots out of there. And when it shoots out of there, there really is no heat exchange because the expansion is happening so fast that there turns out to be a decrease in temperature, very much so. And when that happens, that water gas or gaseous water has a decrease in temperature and it turns into snow. So let's keep on talking about enthalpy though. Enthalpy, if you think about the letter H, is heat. It's to quantify the heat flow into or out of a system that occurs at a constant pressure. So recall, enthalpy is occurring at a constant pressure. So when we say Q, which is heat, with a little p subscript, that's enthalpy. It's at a constant pressure. Remember on the previous slide, we had delta U was equal to QV, V, so that was the heat exchanged at a constant volume. But when it's at a constant pressure, we also have to take into account the work. But let's think about enthalpy, for example. When a chemical reaction occurs and heat is exchanged, that meant there was something changing, and this delta means change in. There was something changing that when it changed, heat was given off. That's what this enthalpy means. So when you look at a chemical reaction, there's reactants and there's products. The reactants had a certain amount of enthalpy, absolute enthalpy, and the products had their own absolute enthalpy. But I couldn't tell what it was because I just have to make it change to see the change in heat given off. And that will kind of backtrack me to those values. And actually, I can never really know these values because I always have to change them to see something happen. So this delta H, then this change in heat or enthalpy, is the heat given off or absorbed during a chemical reaction at constant pressure. So when ice melts, check out this figure over here. When ice melts, it's going from a solid to a liquid, and that's endothermic. Heat is being absorbed by the system to the tune of 6.01 kilojoules per mole. Now, how can I figure that out? I mean, I can measure a temperature change. And when I measure a temperature change, I can equate it back to joules. And I'll show you how that's done a little bit later. But in this situation, that's endothermic. The delta H is positive, and that means endothermic. And there's an increase in the energy of the system. When it's the reverse of that, and something occurs where energy is given off from the system to the surroundings, that is an exothermic reaction. And that exothermicity shows up as an increase in temperature of the surroundings, and that the enthalpy ends up being negative. So recall those little graphs, and I was showing you this is an exothermic graph. These are the reactants over here. These are the products. That enthalpy change was right here, this delta H. And remember, a delta means change in. So that means that the enthalpy of the products is lower than the enthalpy of the reactants. So just put numbers with this. Say this is 10 and this is 50. If that's the case, your change in enthalpy is negative 40. Over here, if we draw the same type of graph, and this is like an endothermic, uh-oh, I messed it up. Endothermic, something like this. These are the reactants and these are the products. And put numbers with it again, just to play with it. If this is 10 and this one up here by products is 50, products minus reactants would be 50 minus 40, and this would be a positive 40 change. So I'm not saying things are always equal and opposite in nature like I've done here with these numbers, but I'm just showing you that the delta H for an endothermic reaction as calculated by products minus reactants is positive. Because remember, that's a state change. So you have the final minus the initial. Products are the final and reactants are the initial. So as far as these thermochemical equations, this is the same picture you just saw. This is the melting of ice. And when we melt ice, it's a positive delta H. The system absorbs heat, and that's endothermic. So when these values are ascribed to a process, I can write this as a chemical reaction, and I write it as H2O solid being converted into H2O liquid. And when that happens, there's a delta H associated with it, and that delta H is positive 6.01 kilojoules per mole. So that means for every 1 mole of ice I melt, I must absorb 6.01 kilojoules. And there's the chemical reaction. If I melt 2 moles of ice, it would be twice that. 3 moles of it would be 3 times that. A half a mole would be half that. So it's an actual value. It's like how much does something cost? If I buy 1 horse and the horse is $3,000, then if I buy 2, it's going to be 6. If I can't buy a half a horse, that'd be kind of gross. But if you could, it would be $1,500. So as far as we just did an endothermic as an exothermic, in an exothermic reaction, heat is given off to the surroundings. It is a negative delta H. The system gives off the heat. It is exothermic, and that delta H is negative. So if we're looking at a chemical reaction way of looking at something, that's why this negative shows up. And when you see it written as energy being given off, that energy would be a product, and you would see it on the right side of the equation. So this is a picture of methane burning here. It's a Bunsen burner. and energy goes in to break bonds. And then when those are made, when bonds are made on the product side, it's more stable. And when things are more stable, usually 9 times out of 10, it's exothermic. So what can we do with these thermochemical equations? We can calculate. So these stoichiometric coefficients mean something. The stoichiometric coefficients always refer to the number of moles of a substance. So this is 1 mole and 1 mole, kilojoules per 1 mole. If you reverse a reaction, the sign of delta H changes. So if you just flip that, this was the melting of water. This is the freezing of water. So freezing of water is exothermic, and that's why when you put water in your freezer keeps on removing heat until it solidifies. When the reaction is multiplied by a factor, the delta H is also multiplied by that factor. And that's what I was talking about before, like my half a horse idea. Or if you just look at your numbers, if I multiply the whole equation up here by 2, then you have to multiply your delta H by 2. As far as the physical states, those must be included, because if you don't include them, then you are going to get an incorrect value, because the physical state of a substance is dependent upon the temperature. And that temperature is an interconversion of heat. So there's your physical state. Here's a physical state here. So as far as, I think this is incorrect. I think that might be 40 kilojoules per mole. But as far as either way, the physical state must be included, because this might be water going to water and water going to water, but one's going solid to liquid and one's going liquid to gas. So let's practice. If I have a chemical reaction, when I burn something, in this example, you're burning phosphorus in air. So oxygen is combining, that's a combustion reaction. And I'm creating the oxide of phosphorus. And remember, the oxidation numbers here are 0 and 0 for elements. And if this reaction has an enthalpy of negative 3,013 kilojoules per mole, that means it's exothermic. But the question is, how much heat is evolved? This is kind of like heat again. It's kilojoules, but it's per mole basis as far as this chemical reaction is concerned. So you notice you have a 1p4 5O2 and 1p4 O10. So if I burn 1 mole of phosphorus, I will give off 3,013 kilojoules to the environment. Now the question is, how many moles is 266 grams? Well, let's do that conversion, grams to moles. Now when we do that conversion, remember, when you have a number that has units, that has a unit per another unit, you can use that to convert from one unit to another. So in this number up here, this 3,013 kilojoules per mole, you could use that to convert between kilojoules and moles and kilojoules. So in this case, you had grams going to moles, but now we're going to use this to go from moles to kilojoules, which is what the question was asking. So the answer is 6,470 kilojoules is evolved for burning 266 grams of white phosphorus. So as far as trying to figure out, this idea of delta H and delta U. Now your book has a section that's dedicated to a comparison of delta H and delta U. So what we're going to look at, remember, delta H is enthalpy, delta U is internal energy. I mean, what is internal energy? Internal energy is the amount of energy the system holds. And then when we change that energy of the system, that can be changed through an enthalpy change, which is heat, and a work. So let's look at the sodium being dropped into water, liquid water. Everybody always loves that reaction because it explodes. So solid sodium reacts with liquid water to make sodium hydroxide aqueous and hydrogen gas, and that's where you get the explosion. Now you get the burning sensation, or the burning from this, because of the heat that's given off ends up igniting the hydrogen gas. So what's being shown down here, here's an actual picture of that happening, is that if it was in here, you had air and water vapor, and you put the sodium, drop the piece of sodium in there, then all of a sudden hydrogen gas is going to show up, and then you're going to end up pushing back the atmosphere, assuming that this has a certain pressure. So remember, that change in the internal energy of the system down here is dictated by the change in enthalpy, which is the heat, and the work done by the system. Now what's kind of weird about this picture is it looks like, here's our beaker of water, and somehow a chunk of sodium is being dropped in here, and then you have all this surrounding space. So I guess as far as this piston is concerned, that the hydrogen that escapes is what pushes the piston back, not the water, the air, not the air around it. So recall, we need to know that work. So if we just run this equation to produce 1 mole of hydrogen gas, remember there's a 1 up here, see the 1 right here. If we ran this reaction such that we reacted 2 moles of sodium and 2 moles of water to make 1 mole of hydrogen gas, we should create 24.5 liters of hydrogen gas. And if we do that, we can calculate the change in volume that's going to occur. And if it's going to expand against a pressure, that pressure we assume to be atmospheric pressure, we can figure out how much energy that work was. And that's what this 2.5 kilojoules is. Now I have a mistake here because this is the liter atmosphere to joule conversion. And to go from joules, I would have had to divide everything by 1,000. And that's where that 2.5 kilojoules came from. So you just have to make sure to check that. So when that occurs, you get this change in internal energy of the system. Now, what was the system? The system was this little beaker of water, and you dropped in the sodium. And when that occurred, you get a change in internal energy that's dictated by enthalpy and work. So as far as this delta U and delta H, remember the delta H that you're seeing on this chemical equation up here was negative 367.5. Now that's determined by temperature changes, not expansion. So you would have to look at it in a chemical experiment such that you could track that change in volume, which would enable you to then calculate the change in internal energy. So energy is lost if you have to kind of add it back in here due to that gas expansion. So as far as our situation, most of the time, delta U and delta H are very similar. And see, if you look at this, look at these two numbers, they are very close. So a lot of times we're like, no big deal. We're just not going to worry about that gas expansion and how it pushes back the atmosphere and then how that's going to change our calculations. Mainly, we're just looking at temperature changes because that's the biggest contributor. So let's do an example as, kind of thinking that through. If you look at, this is an example out of your textbook. And the goal was thinking, well, if I burn this methane, or actually this is not methane, this is carbon monoxide. It's funny that carbon monoxide burns, but it will burn and it will make carbon dioxide. I don't think you can burn carbon dioxide because it's already completely oxidized. But you can burn carbon monoxide. So if we burn carbon monoxide in the presence of oxygen, the enthalpy for this reaction is negative 566.0 kilojoules. But the question is, what's the change in internal energy? Now remember, when there's a change in the number of gases, then there is an expansion or a compression. In our chemical reaction here, look over at the reactants. In the reactant side, we have 2 moles of carbon monoxide reacting with 1 mole of oxygen to create 2 moles of carbon dioxide. So if you look at this, there's a change in number of moles of gas, and that's what this is showing here. The final number of moles of gas is 2, the initial is 3. So you actually get a decrease in the amount of gaseous molecules as this reaction proceeds. So since you get a decrease, you're going to get like a little bit of a compression, right, of the surroundings into the system. So by looking at, remember that delta U, delta U was equal to delta H minus P delta V. Now that delta V is a change in volume, and that change in volume is directly related to the change in the number of moles of gases. And so using PV equals nRT, remember the nRT, that's where this is coming in. So if we know the change in the number of moles of gases, and in this case we do, we're assuming that we're stoichiometrically combining 2 to 1 to get 2. So we know our change in number of moles of gases to be -1. We can take that into account, and then we can put that in our calculation of change in internal energy. Now it looks like our delta H here, remember, was negative 566. If we do this calculation, we see that the change in internal energy is slightly less. Actually, it's slightly more, isn't it? Negative 563 is higher, is more positive than negative 566. And that's because there's a compression going on. So it's like the system gained energy. So anyway, what I did want to point out here is that this -1, when you know the change in the number of moles of gases, it doesn't. We did stoichiometric amounts, so we just looked at the coefficients. But if you're actually running an actual reaction that maybe you start with a certain number of grams, you can still calculate the number of moles of all the gases and still get a number here. It doesn't have to be a whole number. You can put, you can run 10 grams of carbon monoxide, 10 grams of oxygen, and then you can determine how many grams of CO2 is produced, and then you can figure out the change in the number of moles of gases. It's all coming back to stoichiometry. So let's look at our fun sheet questions. Our fun sheet questions in this one is all based around a problem in your textbook that talks about alcohol baths. And alcohol baths were used to decrease the body temperature of a person with a fever. And you would rub the person down, and then as the alcohol evaporated, that would steal energy or heat from the person. So as far as this fun sheet question, I give you the chemical equation that's describing the change. And that change is ethanol liquid going to ethanol gas. And when that happens, you have an enthalpy of vaporization of positive 42.2 kilojoules per mole. Is this evaporation occurring at a constant pressure or a constant volume? So I'll let you think about that, because here, if you're a person laying there, and you're not feeling good, and somebody's trying to give you an alcohol bath, and then as that is evaporating, it's going from liquid on your body to gas. There's pressure out here as far as the atmosphere is concerned. But does the pressure really change when this process is occurring, or does it remain relatively constant? That's what this is asking. Now on letter C, letter B was, is it constant pressure or constant volume? Letter A was explaining the change in temperature based upon this value, this enthalpy. And letter C is asking if you actually put a certain amount of alcohol on the person, and you can put a decimal here. I feel like I should have 250 to give you some more significant figures. If you have 250 milliliters of alcohol and it all evaporates, how much energy was taken from the person? How much heat exchange is occurring? So remember, you have an amount, you have a volume, and you have a density. And if you have a density and a volume, you can determine grams. So you can go from density, you can go from volume using density to grams, and then from grams to moles, and then from moles to kilojoules using this value. Because remember, that's a kilojoules per mole. So if you know how many moles were evaporated, you can know how many kilojoules were stolen from the person's reservoir of their body. So continue on with that. Remember that when we have a person here and he was laying down, he was feeling sick. He wasn't dead, he's just feeling sick. And then you put that alcohol on there because you wanted to remove some heat. When the alcohol was a liquid, the question here is, what is the initial volume of the gaseous alcohol? Was there any gas? That's the question here. And once you figure out the answer to this problem, letter D here, the question is, what final volume would the gaseous alcohol occupy? Because remember, this is ethanol. I'm going to call him ethanol. And the ethanol was a liquid. And when the liquid went to a gas, it's ethanol gas. The question here I was asking you is, what's the volume of this gas? Well, we knew how much ethanol we started with, remember. And since if we can know, we knew by density, we knew the volume. Remember, it was 250 milliliters. So I could use density to get grams, and then I could use molecular weight to get moles. And once I have moles, I can use PV equals nRT to calculate that volume, and that would be the final volume. This guy up here would be the initial volume once you figure out the answer to that question. And then once you figure out the answer to both of these, you have two volumes and you can calculate a change in volume. And I've asked you to calculate the work done in Colorado Springs as the alcohol vapor expanded into the environment. Now it's Colorado Springs, so let's use on the fun sheet here, we're using 600 millimeters of mercury as our pressure. So recall when you're asked for work is equal to minus P delta V. So you want to use that pressure here and the delta V that you figure out from letters D and E. So we're keeping on going with this, and now because the goal here was to figure out what was the change in internal energy of the system of that liquid alcohol. So remember, we have a Q plus W. On the previous slide, we were talking about calculating W. And also on the previous slide, or the one before, we calculated Q, remember, because we were figuring out how many joules was absorbed from the surroundings as the alcohol evaporated. So once you know those values, you can just plug them in. But you want to remember to figure out, was your Q, was it positive or negative? Was your W positive or negative? You have to think about that before you plug it in over here. And then finally, just to drive this point home, there's different ways we can look at this. And this was, we did an example of using delta U equals delta H minus RT delta N instead of delta H minus P delta V. Remember that if we knew the change in volume. But let's just do it a different way. I'm always a fan of saying, well, if this is true, then I should be able to do it a different way. And your book goes through many different formulas on how you can do these things different ways and how they're related to each other. So this delta U, remember, is Q plus W, and this is a work right here. And this is a work because there's a change in the number of moles of gas. So your goal is to figure out the change in the number of moles of gas for this scenario that we have been working on. And I remind you here to use the actual number of moles of ethanol, because in that example problem, we were assuming we use stoichiometric amounts. I don't think we use stoichiometric amounts in this example. So recall that I think you've already figured out the number of moles of ethanol that evaporated. So you can just pop it in right there, use the temperature that we already defined in this problem, and R is the gas constant, but instead of using the gas constant in liter atmospheres in Kelvin mole, you should be using the 8.314 joules per Kelvin mole. Now you got to be careful here, because if you use this R, it's going to end up in joules, whereas the delta H is in kilojoules. So make sure you make the appropriate conversions before you do a subtraction. One more slide here. The goal was just to give you some further practice, like for the final exam, and see how well you understand what's going on. So I'll let you guys work on this one. But again, it's looking at gaseous reactions. 1 mole of H2 to 1 mole of Cl2 makes 2 moles of HCl gas. There's a delta H that's associated with this. It's exothermic, right? You see the negative sign right here. And then this is questions asking you if 7 moles of H2 react with 7 moles of Cl2. This one was H2. To form HCl, what is the change in internal energy for this reaction? Now there's a trick question here a little bit, because you'll kind of see that 1 mole of a gas and 1 mole of a gas makes 2 moles of a gas on the reactant side and 2 moles of gas on the product side. So your change in volume would be 0. So that makes your life a little bit easier as far as doing the calculation for the number of the change in internal energy, because change in internal energy is equal to Q plus W. But if there's no change in volume, I don't think we have to care about that guy. We only have to care about Q. So go ahead and give that a shot. And if you have any questions on that or the other previous questions on the fun sheet we were just looking at, shoot me an email.